until it says recording. Okay. All right. So welcome to the class. My name is Rashada. I'm a professor at TGGS, and I'm going to teach computer architecture, which is basically my own area of expertise. If you're wondering what the heck is computer architecture, basically we build computer, right? So in this class, we'll go into conceptual things that describe how we design a chip, a microprocessor, as well as the actual practice to figure out how are you gonna design one, what's the process of actually coming up with such a design, and how can we prove that the design that we are showing is better than quote unquote previous state-of-the-art design, right? So first thing first, let me switch over to, so this is one thing I hate about Microsoft Teams, which is I cannot really have the chat opening up. So I'm gonna basically alternate tab between my own screen for PowerPoint and your chat, right? So if you have questions, I do encourage to just turn on the microphone and ask. I'm gonna do a quick break between a bunch of slides so that you can ask questions. There'll be a pause. I'm gonna say, hey, you have any question, anything that have question about the slides. Whenever I ask that, it typically means that the slides that I'm talking about is likely to be important. So I want to make sure you understand that. But I had to tap between the chat and the actual slide. So you might hear me basically clicking on the keyboard. There might be some noises. Basically, it's me tapping between the two windows. All right, so here's the deal. Today we'll talk about the intro stuff. What's my expectation of you? And we will cover kind of like what is architecture and where we have been in the history, basically history of computer science and computer engineering as we know it, right? So before we begin, right? So by the way, do you all see the slides? And including the transition, right? Because sometimes Microsoft Teams is also bad at like making sure things transition. So if the slide doesn't move on, let me know. It's like somehow Microsoft managed to like make the worst meeting software out of like Zoom, WebEx, and everything we have. And it just happened that our college picked this one. Bad choice, I guess. I didn't expect that they can make it such like this poor quality. So before we begin, the class is basically, we will talk about what the class is going into, right? So that you know what you're getting into. So I have to also make sure that you are aware that after today's class, and you're like, hey, this class is not for me, like, is it too in-depth in the area that I don't want to listen to? You still have a choice of like maybe signing up for another class to make sure you can pick. For OPAD, I'm sorry about that. You are in a different curriculum from your friends here. So you have to make sure you pass my class, right? So I really, really want to make sure you pass my class. We'll talk offline a little bit as well. Make sure that you can do the lab from last year. It's the same thing. Make sure you can do that. That's basically the main requirement to pass my class, right? So please make sure you can do that. One new thing from last year is I have homework 0. The reason why I have homework 0, that is due next Thursday, is to make sure you have the prerequisite to actually take this class. So everything in homework 0 should be really easy. So for those of you who have the background, it would be a good refresher exercise for all of you to know how to program in C and how to use Linux to do Linux like shell scripting. If you find homework 0 hard, you need to catch up in a week, because we're gonna ramp up. Everything that we have in homework 0 is essentially equivalent to first semester sophomore or second semester freshman class. So everything we ask over there is really, really, really basic. If you find that hard, you might want to reconsider being an engineer for computer engineer. So if you find it hard, catch up. That's something you have to catch up. Otherwise, no one will employ you as a computer engineer. It's really easy, but it will be a good refresher course for this class. I'm gonna post recommended readings, and I'll make sure. So I'll try to keep this more up to date for this year. But the list is actually from last year, and I already make it such that it's actually really thorough for all the topics we cover in this class. So it will be papers on the fundamental topics that touch each of the subtopic that we learn in this class. All right. So if there are new paper that are interesting, I'm gonna keep it updated. But otherwise, the recommended reading list right now is really, really updated, and these are recommended readings if you want to dive further into the topic. Okay, so admin stuff. I'm gonna skip who am I a little bit, but this is just briefly a brief overview of myself. I'm a lecturer here. I got a PhD from Carnegie Mellon under my advisor Ono Muslu. A few disclaimer about my advisor. He actually has the most number of publications than anyone else in the world. He's one of the world leader on DRAM architecture, how to build new type of memory. If you want to look into this area, he's the guy, right? We also work on GPU. I have put, so this number is not updated. So we are actually ranked number 9 in Asia, not number 8. So CS ranking is the top ranking site for computer science and computer engineering. The good thing about that is if you want to go into a PhD, that site have a breakdown for each area, right? So I'm one of the leader in computer architecture in Asia. So they also have a breakdown for each of the professor in computer science, basically. That includes the personal website, that include the publication that each of the professors have done. So if you go there, you will see that, for example, Carnegie Mellon is like basically number 1 in computer science. And if you look at the breakdown, you see for each of the professor over there, what have they done? You can check out places like MIT, Michigan, which is also the world leader on architecture, for example, right? Or Stanford, Berkeley, like this top university. There'll be a link to each of the professor website. And one nice thing about this is that unlike the other ranking site that kind of counts like a lot of these things like, okay, how much funding do they got? These sites only count top publications. So unless you have a publication at the best venue in the world, you're not going to get counted, right? So this is really catered toward PhD students. If you want to find someone you want to work with, that's a really good resource. Here's my website and here's my email. Office hour to be determined. We have a TGS Discord. Are you aware of that? I guess not. So I make a Discord server. How many of you here use Discord before? So we all use it. Okay, so at least you are my generation. Yeah, I've been talking to like my colleagues, and they're a different generation. So they grew up. Sorry, they grew up in a different generation where communication software is limited to things like Skype. So I built a Discord server. I pitched it to a bunch of lecturers here at TGGS. A few of them actually like enroll most of their students in the lab already, so that they embrace the technology and they love it. So in ESSE, it's just me and Dr. Yost use it so far. Even though we are, we change to EC. Even though we are supposed to be more on the technology side, somehow it's just me and Dr. Yost who are using Discord and not embracing technology. I'm trying to change it. So we have our Discord channel. I'm going to send you the link after the class. I'll post the link on our announcement in the class website. This will be where I'm gonna hold office hour. The reason behind that is because you can freely share your screen. That's the first reason. The second reason, with COVID, you're not gonna be able to talk to your friends face to face. This is kind of like the second alternative. So there'll be hangout room. I should make room like let's go eat kind of channel or like board games or even like online games. Just go in there and hang out, guys. COVID has already make things like depressing. So use it to your advantage. So if you find like, okay, your life is miserable and you haven't met anyone in a while, ping me. You can see me online. Basically, just shoot me a message. I would like to believe that most of us as a lecturer, we don't have this weird like wall between like I'm a lecturer, you can't talk to me. No, we're not. We're human. So if you have any problem, you have any concern, if you have anything, just let us know, right? And if you have any feedback, also do let us know so that we can fix these together to make your life better, right? We are all in this like new pandemic that no one know how to basically manage. It's been a year, so we're doing better at managing the pandemic, but there's still things are changing quickly. Wrong turn, by the way, it's getting worse quickly. So make sure you stay at home and keep yourself at home. It's really dangerous. So for Muhammad, just in case, since you're an international student, so if you haven't really like, followed the news, it's really bad in Thailand right now. It's like, I think our per capita situation is worse than India at the peak right now. So put that in context in any way you want. And in the next semester, I'm gonna basically also teach research methodology class. I'm gonna use some of these example of fucked up in the medical area in Thailand that are related to research and why we are in this situation right now because of like old doctors who doesn't really listen to actual science. I mean, for Sahasawat and Opar, you're probably aware of who are these guys. And for Muhammad, I'm gonna show and probably an actual case study on why these are wrong and why you should not do research this way. It's just wrong. All right. So anyway, TGS Discord is used and among students. I know we don't have a lot of students, so we are trying to build a community. I'm trying my best to get alumni to join us so that if they have job posting or interesting talks and things like that, they'll be put it on there. So I hope this grow into an actual community, right? So now it's your turn. So I mean, Opad, it's the same deal. I'm gonna ask you, who are you? What do you want out of TGGS? And please be honest. I mean, come on, guys. I know that a bunch of DAD students just want to be here because they want to go to Germany. Just say that. I mean, we want to help you. Come on. So yeah, your turn. I'm gonna pass the mic to you while I'm basically showing my breakfast. So yeah, who want to go first?
Okay, so my name is Mohammad Ashraf and I'm from Pakistan. I have a bachelor's degree in electrical engineering and this is my first semester here at in TGGS. And what I expect out of TGGS is just to polish my skills and to have an international exposure in uh, by interacting with international students. And yes, honestly, I obviously want a dual degree and then a good job in Germany. That is why I ought to choose this program. And as far as this course is concerned, uh, I was a part of a team here who was developing ventilators here in Pakistan due to the lack of ventilators at that time. So in that product development, we studied that there is some kind of documents like software architecture documents, hardware architecture documents, and we have to submit that documents to get our prototype approved. So at that time, I came to know that we didn't study that in our electrical engineering before. So at that time, I developed my interest in these architectures so that whenever I develop some kind of product, as an engineer, I should have a knowledge of these things. And secondly, I read the course contents of this course, and I found that very interesting, specifically multi-threading, multi-processing GPUs, and uh, and working in Linux, because I think we have more control over the threads or the processes in Linux as compared to Windows or some other platform. So yeah, I'm looking forward to have a very interesting course in this class, and I'm motivated to learn as much as possible.
All right, awesome. Thank you for the introduction. I believe you're a TAD student, right? Because I remember I read your resume for sure.
No, I'm an MS student. I have only a bachelor's degree in electrical engineering.
No, but are you DAD?
Yeah.
Okay, okay, yeah. So welcome to TGGS. So one quick thing that I want to mention about DAD, that I'm gonna go against many people in TGGS, but that's my belief, is a lot of people in TGGS, especially if you talk to professor who somehow graduated from Arkan, I don't really agree with that policy, which is like, go look at the lab or institute at Arkan and look at what they work on. So that's the part I agree. Look at what they work on, but don't always focus on every single paper that they're writing. Arkan is here. The world is here.
Yes.
There was a big gap between the technology side where Arkan is and where the world are. So my recommendation is not just go look at the institute and work that they're doing. That's a given. You have to do that. But check out the best in the world, right? If you want to look into more of like the blend between electrical engineering and the hardware, like basically kind of blend in the circuits, right, into computer system, check out MIT. I mean, you all heard about MIT. It's like one of the best engineering school in the world, right? Why not? So this is how you're gonna basically make yourself more valuable to folks at Arkan, because you just don't know, on top of the things that you are aware of what people at Arkan are working on. That's a given, right? But you also know where's the state of the art, right? So that's my advice for you. And again, I'm gonna go against many of the things that lecturer here tell you. Because if you talk to people who graduate from Germany, they always focus on, oh, check out what the institute is doing and look at what they're doing. Look at this like super narrow rat hole of like things that they're working on. Broaden yourself, make yourself motivated, follow your own passion, stress on your own passion, right? And make sure you can basically figure out where and what institute that you want to work with, right? And find a middle ground. Because I mean, I'm also new. I'm like, this is my second year here, right? So I don't have a lot of network with Arkan. I do have, though, at the end of the presentation, I'm gonna show you where are my collaborators that I've been working with, right? So I'm familiar with the world. I'm not familiar with Arkan, but I talk to them, and they're researchers. They're like us. I mean, it's the same thing. If there's interesting idea, they're gonna pursue those. The key here is you have to make sure they are interested in what you're working on. So that will be my advice. So hopefully, this kind of trigger, hey, I want to work for my own sake as well. Don't just listen to whoever told you that you must work in this certain area. That's also a good idea. I mean, to be honest, once you graduate from bachelor degree into a master, right? You most of the time, I have to assume that many of the master students still have no clue of what they want to work on. So that's definitely a good start, right? That's definitely a good start. My advice is also explore. It's time to explore. You are in a university setting, so you can explore. For example, OPAD can tell you once you join a job, right? Once you join a company, they're gonna limit the choice of like what you can work on. OPAD is a scholar from Western Digital, so his work would focus on hard drive, right? But in your case, Mohammed, you're in a university setting, you have options, right? So take advantage of it. For OPAD, for example, now then you take advantage of things that you can contribute back to Western Digital. It's a different scenario. Anyway, so thank you for your introduction. So I guess either Sahasawat or OPAD, your turn.
Okay, do you hear me? Yeah. Okay. My name is Opad Gopan. I am the third year student. For what now from TGS is I want to graduate and get my new knowledge about technology and some computer or hardware or computer skill. And what I want for this class after last year I want to improve my learning skill or just uh, improve my computer skill or coding. And the special topic I want uh, in this class, I want to know more about the multi-thread computation or parallel computing, because it's if I understand and I can use the parallel computation with my algorithm, that I want to improve the efficiency and decrease the processing time. I think this thing will help to improve my algorithm for yeah, this is the topic that I want. Yeah.
Okay, great. So since two of you already mentioning multi-threading, so I'm gonna make sure I note of that, because at the end of the semester we have time to like kind of explore some topics. Sorry, also my cat. This will happen quite often throughout the semester, that my cat will take over my keyboard, my desk, and somehow my monitor. So I'll just you see them around. And I'll make sure at the end of the semester we have that. OPAD, I actually have some ideas that would work for both your project for this class and your project for your thesis that are related to multi-threading. So you were basically we were talking a little bit last time about what you should do for the project, right? And we kind of like also almost narrow down to the things that you should work on. So this semester, I want to make sure we kick that off early. And since this is like let's sync up offline. I'm gonna send you an email, and I'm gonna propose a couple of things. Give me a second. My cat is like vomiting. I'll be right back. Yeah, sorry. One of my cat has been tricking everyone in my family that she hasn't eat yet, so we keep feeding them. And she just vomit like 2 times now because she eat too much for the past day. And now she's staring at me right at the food plate. Does she want food again? No. Anyway, so we'll sync up offline. I want to make sure you done with our program and graduate, right? Okay, so what's your turn?
Good morning. My name is Sasavat Pongsanan. You can call me Mac. I would like to study more during working situation is unsafe condition. And I want to understand better the structure of computer, better processor, graphic, and more. And I interested in GPU. Yeah. Thank you.
Okay, awesome. So I'm gonna talk about the GPU. I think I think the GPU is a big part of our lecture. I think it cover probably at least one full like 3-hour lecture. I want to double check. So you graduate from the like full-blown electrical engineering degree, right?
Yes.
So make sure. So this is one thing that might concern me a little bit. It's like your background in coding. So make sure if you find certain things hard, let me know topics that you find hard so that I can find the background material for you to, for example, watch, and so that you can catch up. Because I want to make sure this won't burden you, right? Because we're gonna keep learning and learning and learning new things, and a lot of things that we're gonna talk about here. Some of them requires additional background. So if you feel like you lack anything or things that I say that like I have no idea what I'm talking about, let me know right away so that I can find the additional material. I do have some preliminary material that I teach at a different college. It's on my YouTube channel as well. So if you're curious, I think I already posted on, I believe I posted a link on the email that I sent to all of you. So if certain things over there, oh, this is new, check it out. Just play it at the 2x speed. It won't take long, right? And I hope that would be a good thing. Homework 0 is also another gauge, a great like gauge to do I need certain things. So feel free to email me. I want to make sure that you follow everything and you learn things that you should learn and you take the most out of the class, right? So the key here is to take the most about the class. And I'm gonna ask the same thing, but I think my assumption is you haven't know a lot of these things. But how much you know about this terminology? If the answer is no, this is a perfect class for you because these are the things we're gonna cover, right? So I think that's all. So these are some of the topics we're gonna cover. This basically govern how do we design a microprocessor and to make sure it runs, right? To design is one thing. To make sure it runs is another thing. To make sure they are fast is like another separate thing. And these days, if you own, for example, an iPhone, you probably realize that sometimes battery run out, right? So energy efficiency is also another big thing. So if you have been looking into things like Bitcoin and discussion about that, Bitcoin make no sense in terms of energy efficiency, which is true. It make no sense in terms of energy efficiency. We will start to learn where does the energy consumption is coming from, right? And the goal of this course is basically to know how computer works. We go back to the basic, right? You want to program a computer. Or what I'm going to say is, if you don't know how computer works, you're not going to be able to understand sometimes why certain thing is fast and why certain things are slow, right? You understand key techniques in architecture and understand the trade-off in hardware design. The keyword here is trade-off. It means that if you have, say, certain amount of money, right? How many of you here run into this situation? I have money. I want to upgrade a computer. Which part should I buy? Right? This is a trade-off. You need to figure out how do I utilize my money. Every single company you're working at would have to design that as well. If I need a new server, what should I buy? If I need to pay for a cloud service, how many compute nodes should you actually acquire and run, right? Be a better programmer and think out of the box. This is the class that would enabling you to think that, hey, I don't have to just change the software. I can change the hardware too. Anyone here heard about the tensor processing unit or tensor core? How about TensorFlow? So you might have heard about TensorFlow, right? Tensor processing unit is a special hardware designed to do this tensor computation. Basically, it's designed to make machine learning faster, right? Think out of the box. Let's change the hardware. It's possible, and people have done it. People have done it numerous times, and these days and age, it's become a hot topic again because of two reasons. We demand more performance and we demand better energy efficiency. These are always the goal of why you want to change the hardware. And what do I expect from you? You're gonna have to work really hard. So this is a given, but well, the work you've been pushing for this inside this class, I can assure you, it actually would be a good background material, so you learn a lot, right? It's not like a bunch of repeated work that make no sense. These are work that are hard, but you learn. I hope you know things like how does logic gate work, like what's the A and B, what's the result of A and B, A or B. I'm not gonna require you to know find the option for this class unless you have a project that has Verilog component, like actual design. Then I'm not gonna require you to learn Verilog. Verilog is a language that we use to build hardware. So in this case, our lab would use what we call a simulator instead. You write codes to simulate the TGGS hardware. Homework 0 would test a little bit about how you program in C, but a basic system knowledge would help, and knowing how assembly work would help as well. You have to be okay with C and Linux. If you're not okay with C and Linux, make sure you're okay with C and Linux in the next 2 weeks. Attend lectures, do all the required work, and by default, if you have to do all the required work, you're gonna have to work hard. Ask questions and participate in the discussion. This is the only way for me to make sure you catch up, right? So ask questions. I'm not the devil, right? Okay, if you look at my homework, you might thought that I'm evil, right? I might be an asshole in terms of like giving you all this work, but I'm human too. So I want to make sure you catch up and understand and participate in discussion. Both in class and on the class website, right? On Discord as well. So basically make sure if you need to catch up to certain things, let me know. Do paper reviews. So in this class, you will all have to do what I'm gonna say, paper reviews. And these are, because this is a master level course, right? So I'm gonna require you to make sure you can understand papers. These are technical papers that sometimes we are not going to expect you to be able to like basically write your own paper all the time, because this is not a PhD program. You're not in a PhD program, but we're going to expect you to be able to read them and understand what they are doing, because this is a common thing. If you go to Google, Amazon, Facebook, Apple, Intel, AMD, any of these top tech company, master students should be able to chew on the paper and know exactly what the paper is talking about, so that you can take parts that are interesting about the paper, implement it and test it, and see if that actual benefit for your own industry, right? So this is common. Do not procrastinate. My homework takes time. Sometimes it's actually just a brute force, take a lot of time, typing time actually. Once you understand what you have to do, it's actually not too bad. But if you procrastinate and work on the last 3 days before the due date, you're gonna have a lot of fun in a bad way. So my recommendation, try not to procrastinate. If you have a lot of conflict, for example, that week you have like 5 midterms, or actually there's no way you can have 5 midterms. Let's say you have 3 midterms on that week. Let me know, right? I'm not evil enough to say, hey, I'm not gonna push the due dates. Just let me know so I can make sure I arrange the better schedule for all you. And I will not tolerate any plagiarism of any kind, right? My earlier policy is you get a negative maximum of the grade, but my new policy, you get it out. Thanks to Alex, who kind of comment on my earlier policy not making sense. And since he comment that if getting a D is worse than getting an F, if you plagiarize, you're gonna get an F. So if I detect any plagiarism, you fail. All right. All right, for the class website, here is our class website. This is where we will all have lecture material posted. Reading list will also be posted here. You need to submit all your required reviews. Anything after, so I think the number here is wrong. So let me correct the number later. It's not 8 reviews. It was from last semester. I actually reduced it so that it's not as many. So we have to do 6 review. 6. There'll be another slide for this. You are required to do at minimum of 6 review. Any more than that is the flat extra credit, 0.25% of the whole grade. So 4 more reviews, basically 1 more % of your entire grade. That's 10% of your exam grade. I would like to have discussion in each of the lecture so that you can kind of like drive the discussion a little bit toward the end of the class, or ask me like, what about this? What about that? So that I can basically figure out what are you interested at and how do I make sure I satisfy your interest. Grading breakdown, this is going to be different from last semester. 30% assignment, that's more. 10% paper review and discussion, that's less. Usually it's 20 and 20. This semester, 30% assignments, 10% paper review. So I want to make sure I put more weight on the actual coding part and less weight on the writing part. 40% project. This is where the majority of your grade would be. Make sure you come up with a project early and check back with me so that we iterate over, is this a good project or not? And most of the time, you're gonna get close to full credit on that if everything goes well. 10% midterm, 10% final. The reason I put the number really low here is from my experience. Somehow you are gonna score about, on average, always like at about half of this. So I'm not gonna make, I will make sure this won't put a burden on your overall grade, right? My exam would test your knowledge. It'll be hard. Sometimes it's crazy hard, but I designed the breakdown such that if you get full credit on everywhere else and you get 0 on exam, you still get an A, right? Our cutoff is 80% is an A. So if you can manage that, you can fail on the exam. But I do not recommend you to fail the exam. Treat that as a contribution toward your overall grade. Why do I have this breakdown? Reviews tell your willingness to learn new ideas. Assignments will tell you you can create something that you learned from the class. And the exam would determine your knowledge of the class material, right? So, and probably your letter grade, right? It is, I mean, in some, that's 20%. So if you do well, actually there are students that did well, like close to say 90% or 100%. So if you did well, you're gonna have a lot of boost toward your letter grade, right? You can even skip one assignment, you'll be fine with the exam. Paper reviews, you expect to do at least 6 of those. Each one is 1.5% of the grade. In total, that's 9%. Any additional review after the 6 is extra credit. And 1% class participation. Basically, attend lectures, ask me things that you do not understand. This is by default free grade. I actually never took any grades out of this class participation thing, unless somehow you disappear from like my lecture, like you somehow is gone, you never attend lecture. That's the percent you're not gonna get. But if you attend lectures, you ask a few questions, you're fine. You can. This is one thing we're gonna do is at the end of the lecture, if someone submit a review, I'm gonna pick those who submit the review to discuss the paper. This is for me to basically train you on 2 fronts, right? First is presentation skill. So that this is really, really, really important. If you haven't realized how important it is, you will once you start a job. And it's one of the skills that most engineering school never prepare you for that. Like we as engineer, we are typically 2 things. We are socially retarded. We are not really good comparing to your colleagues in the social background, right? At socializing. So if there's a big conference, we tend to hang out in the corner and talk to your close friends and not talk to anyone else. So that's what we're typically bad at. And just be aware that we are all aware that we are bad at it. So when you hang out, just keep that in mind. No one judge you on anything. The second thing is we are typically bad at presenting and conveying our idea, right? We build things. These are important, but we also need to communicate to people why the things we built are important. So this is really important. Let me expand on paper review a little bit because I want the review to be critique rather than a summary, right? Every single paper has a flaw. Every single paper has a flaw. So your review should not just have the summary of the paper. I want you to keep digging deeper and look into what's a good thing about the paper. These are going to be easy because the author would tell you what's good about our mechanism, right? But the downside is harder. I want you to go beyond like, okay, this is hard to understand kind of comments, but go into like, technically, if I assume the same setup on a different system, but will something break? Are there certain assumptions that make no sense in real world? Did they evaluate a complete set of representative workload and things like that? Basically, make sure you critique the paper, you critique the paper's idea without attacking. That's many ways to critique the paper without attacking the paper. And what can you do to improve the idea further? This is the think out the box part, right? So try your best to do that. Your first say, typically what would happen is your first say 3 reviews will not be doing this. I'm gonna go and check and grade and give comments so that you can dig deeper and take my feedback and figure out how to actually access a technical paper. I will read all your review. Sometimes that is a lie, but I'll make sure I read your initial like 3 or 4 reviews, if not 6. And I'm gonna give you detailed feedback. In the later review, I'll read them, but I might, if they are good already, I'll say this is awesome. And if there's clear flaw, I'll let you know. If there's no clear flaws, like this is awesome, 100, and pass on. And I'll look at the effort that you put in the review. Don't plagiarize. Don't plagiarize because you're gonna get an F. When I say plagiarism, don't copy text from the paper onto your review. My recommendation: close the PDF of the paper, type using your own word. Right? Type using your own word. I mean, I'm from Thailand, so for sure I know the capability and what are the typical mistakes that Thai people have. For example, on your own writing, right? So I can figure out whether this is original writing or is it your writing. The reading the paper would give you background knowledge, the idea for a project, and how to improve your technical writing skill. This is another key thing. Again, I know this is a lot of work. I want you to make sure you learn. So if you're not signing up for a lot of work, you still can drop the class. That's your choice. But if you're going to stay with my class, you have to work hard. The reason why I make sure you work hard, this is not even as hard as a class that many of your colleagues from somewhere else in the US are actually going through. So I want to make sure you can compete in the international level, not just in Thailand or in Asia, right? This is basically to make sure you can have a choice. If you want to get out of Thailand and go somewhere else, awesome, yay. And don't plagiarize other articles. So assignments, you have a few assignments. This was forced you to apply concept we learned in class, and generally what we're going to ask you to do is to implement parts of the simulator that simulate real hardware, right? What do I mean by that? Initially, you'll be given skeleton code and you are going to implement some basic features of things we learned from our class. And your solution will be used as a starter code for the next assignment. By the way, so assignment 1, make sure you finish them because you're gonna build assignment 2 will be based on assignment 1. Assignment 3, you're gonna get your own starter code. So after assignment 2, you're done with that code. Assignment 3 will be a separate piece of code. Hopefully, this is gonna help you with your projects because after you finish assignment 3, one option is to build certain things that we learned from the class on your assignment 3 as your project. There'll be a lot of topics we cover. Our 3 assignment will cover only initial parts of the lecture. We are not going to cover things like main memory and things like that. So you feel free to build that onto your simulator. Class project, everyone expect to work on one final project. That will be 40% of your total grade. Expectation is this will be a roughly 2 months worth of project. I can judge whether this is a 2 months worth of project or not. It has to be related to material we learn in this class. That's the proposal comes into play. So I can figure out, okay, is this related or is this like some project that I'm not supposed, it doesn't have to do with anything in our class. And you have to provide your own contribution somehow. You have to build things. And check with me on some ideas. How do I get ideas for a project? Think about what's missing from our assignments. Things we learned that we haven't talked about, right? You can read paper from top tier venues. If you want to figure out where's the top tier venues, talk to me, especially in computer science. I typically would be accurate on anything computer related on where the top tier venues are. For those who are Thai, you might have heard about journal, right? I would have to tell you, in computer area, journal is crap. Top tier venues are in the conference where CTO of Facebook, NVIDIA, Intel attend. These are where the real top tier venues are. Researchers in computer science in Thailand are aware of this, but the other researcher who kind of govern the policy inside this country, they're not aware of it yet. They thought journal is the best. It applies to most area in the world would actually publish in a journal. Unlike us, we have our own top tier, like I would say Nature's equivalent of top computer science research work, right? Where the best go to. And that's why CS ranking is so important because it actually only counts those top tier venues. In our area, computer architecture, we're going to look into these 4 conferences. ISCA Micro is a top tier venue for architecture, like the traditional architecture. ASPLOS is where you blend in computer system, programming language, compiler, and architecture together. So this will be more cross-discipline. And HPCA is more on the high performance computing side. Sometimes people would think HPCA is like ISCA Micro tier 1.1, which is not the same tier, but still top tier venue. These are the absolute best conferences for computer architecture papers, and take advantage of myself. I'm gonna expand on that toward the end of this class. Check out the class website and contact me so I can conjure some idea that would be relevant for your project that are not too hard, should be done by 2 months, and doable. So check back with me is the first gauge of whether it's doable or not, because I've been through a lot. So I can figure out, is that too hard or is it doable? Talk with people who have taken this class before would be another good resources. But I'm gonna, so basically this is my 3rd time teaching this class. So the random cat scratching the window, sorry, got distracted. So the way I make sure the project is done changed a lot. The first semester is too open-end. I ended up with a lot of students that just ended up trying something that's too hard. and they just managed to install the simulator. That's all. So too hard of a project, we got nothing. So I'm gonna basically changing that over and over. Project checkpoint. Early September, you're gonna have a Q&A and kind of like a first draft of your proposal up. This is when you're gonna check with me, like, okay, can I do this? Can I do that? Mid-October, we'll have a checkpoint. I'll basically checked where you are, so that if you are behind, I can ping you and say, hey, this might be a little bit behind based on the scope of your project, so you might want to ramp up. Or if you're way ahead of the project, I'll tell you, okay, this is awesome. If you want to go further, it's good enough. But if you submit what you have right now, you're at like maybe 80% of your grade already. So good job, and make sure you finish the rest of the project. Last week of class, you have project presentation. The one different thing that I'm going to do this semester is I'll probably send an email to everyone in TGGS and invite them to join. I don't expect them to actually join, but just in case we have one or two more lecturers, sorry. And oh, sorry. I don't know what's up with my cat today. And the report. So you're going to have to do the presentation and the report. Typically, after the presentation, I'm going to make comments on two things. The first thing will be on your own project and the technical side of things, right? The second thing I'm going to put in also comments on your presentation skill. This won't go into your grade, but it will be a good feedback on how to make a slides, how to do presentation. So presentation skill won't go into your grade, but I'm gonna make that comment anyway, just for the sake of like, your feedback. You're gonna have 5 late days in total, and you cannot use these late days on the project presentation or the project report. How does the late day work? Let's say you have assignment 1 and you cannot finish it by the deadline. You have up to 2 days that you can use for the late days. Basically, this means that across the 4 homework 0, assignment 1, 2, and 3, you have the choice of going 2 extra days for each one of them, and 5 in total. This checkpoint basically help you prepare for the final report. I'm gonna provide you the LaTeX template. If you're gonna do anything in computer science, you need to know how to write a report in LaTeX. It's a lot better than Microsoft Word. Do it as best as you can. This is a practice for your master's thesis. Feel free to contact me. By the way, we have our own students who kind of port everything from the Word template into a LaTeX template for your master's thesis. That guy's name is Lucas. He was the student who enrolled with us last year. He's, I think, doing internship right now. So if the academic affairs basically checked and the template passed them, basically this is likely to become an official LaTeX template. So if that's the case, you can now use LaTeX for your own master's thesis. It's much. So once you know how to use LaTeX, it's actually a lot easier compared to Microsoft Word when you have to do formatting, making sure everything is beautiful. So that's it for the initial part. Any questions before we go into what is computer architecture? Okay, it's just no question, so let's proceed on to the material. I'm gonna do a break about I would say 40 minutes in from this point to make sure we have a break. So every single class, I do not believe in the effectiveness of 3-hour lecture. Too long. I'm gonna do a break in the middle, but if I'm going too long to the point that you start to lose focus, let me know. All right, because I don't mind taking a break. I just want to make sure we have a proper cutoff between each break. So this. Oh, Pat, I forbid you from answering because you've been through this slide before. It's the same slides. Anyone seen this before? Anyone here heard about the Louvre? The Louvre Museum in Paris. So if you go to Paris, this is right in the middle of the city. This is the entrance to the Louvre. So if you want to visit the Louvre Museum, which is, I went here. So this actually, I took this picture when I went there for a conference. So good side about our field, many of the top work are presented at a conference. So you get to travel afterward as well. This conference, you have to actually go there and join them and present your work, right? So this is a conference that happened in Paris. I ended up staying 2 extra days. I had time to visit the Versailles, but I do not have time to go down the Louvre. I managed to go there in the evening. I took this picture. This is the entrance to the museum, and the building behind it that you see is actually a part of the museum. It's actually, once you're in, you have to go underground, right? This, if you think about it, right, the reason why I can take this picture, and it actually does look okay, ish. So it actually, to be honest, looks much more beautiful in real life, right? It's a single piece of really awesome architecture. This is an architecture masterpiece, right? If you think about it, who would have thought, like, I'm gonna build an underground museum with a pyramid on top, a glass pyramid that's surrounded by another really like, I want to say Renaissance looking, but I don't even sure what kind of styles is that buildings, but it look really like Europeans, right? These are traditional buildings that I believe already there, but the entrance is probably built by the architect, right? Everything blend together. This fountain actually surrounds the entire entrance. The entrance is actually right here. So you walk in through here, right? The rest are just fountain. So you can take this kind of picture, right? They thought about the lighting. They thought about how it would look. They thought about the functionality. It protects the whole museum because everything is underground, right? Because everything is underground, so it's kind of protected, right? So this is what architects is doing. Another thing is, so what is this? A waterfall, right? It's a waterfall. I say this is a place. It's called Cucumber Fall. It's about 1.5 hour drive from Pittsburgh. Pittsburgh is where Carnegie Mellon is. So I spent 13 years in Pittsburgh since my undergraduate degree into a PhD and 2 more years of postdoc. So I visit this place a couple of times. What if I have a rich guy say, hey, I want to build a house on a waterfall? And this actually happened back in the day, around the time where Pittsburgh still, well, we have a nickname. The city of Pittsburgh has a nickname called Steel City. The reason why it's called Steel City is it used to be a huge hub for the steel industry. We actually, our American football team name is the Steelers, which actually we do have a lot of the NFL win, right? It's one of the major team in the US. And back in the day, I'm not sure if you heard about the guy named Andrew Carnegie. So Andrew Carnegie is a tycoon. A tycoon is basically a business guy who is really rich and own a big industry. If you're Thai, think about the CP company, right? But unlike CP, Andrew Carnegie, towards the end of his life, he actually donates like so much of his money to philanthropists. He's more like a Bill Gates kind of guy, where he might have done a lot of things while in the business year. And then toward the end of his life, he did a lot of things to like do donation for academic research, build university. That's where the Carnegie Mellon names come from. He actually built the university and actually made sure that goes to education, right? So back in the day, there's a bunch of, so Pittsburgh is a relatively big city. So there's a bunch of tycoon over there. There's one of the tycoon say, hey, I want to build a house on a waterfall. This is called the falling water. So it's close by from the waterfall picture that I showed you earlier. It's really close by. It's one of the same like river system in the river called the Ohio River. And this is a building designed by one of the major architects of the US called Frank Lloyd Wright. So if you look up his work, he dominates a lot of the huge building projects back in his day in the US. Many buildings are actually built by him, designed by him. Many other buildings are inspired by his design, right? So this is already being enrolled in the UNESCO World Heritage Site. You can go there and take a tour, and the tour guide will actually let you know how the architect designed this building to match the user's demand. They would like to use this as the house where the owner can house a bunch of guests, so that they can actually use the waterfall to kind of relax. There's also a guest house in the back, but you can basically they design it such that you look at the beautiful part. If you enter from the front, you don't see the guest house. You have to kind of go a little bit up to see the guest house and things like that, right? So how about computer architect? Similar to the real architect, we design computer, right? We need to, first of all, understand the circuits. We need to fundamentally understand the software. We are the bridge between electrics and electrical parts to program. And you build the machine that would match the user demand, right? Because if you build a hardware that no one uses, it's not going to be useful at all. So you need to know what's the demand from the user. So in order to evaluate a design, is this a good design? This is what you have to do. First of all, what's the performance? It is fast. Is that fast? Are you going to buy a chip that are fast? Do you like a chip that are fast? The answer is always yes, right? I will always want my computer to be faster. Worst case, I'll use it to play games. And I do play a lot of games, right? Functionality. Can I use it to program the multiple things? Or are they going to be more like a GPU where if the program exhibits certain behavior, they're going to be fast, but for most of the program, they're going to be super slow on the GPU. How much are you willing to pay for a computer? Usability, again, this is almost the same as functionality, but functionality would also cover what can they do. But usability is more like, can I use it? Right? And many other trade-offs, such as energy efficiency, power, right? For example, if your phone is driven by a battery, if you're in the electrical engineering background, you know that battery has its own peak power. It can't go beyond certain watts, which means that if you want to design a computer, it never have to, you have to make sure it never go above that wattage. Otherwise, you can't power it on, right? So these things would govern what can go into the design. So these are always the key goals in designing a good computer. And our job is to identify them and achieve these goals without breaking your bank, without breaking your bank account. So how to be a good architect? This is an adaptation from Yale Pat lecture. Yale Pat is a prominent architect even now. He has a lot of work that goes into a real chip, including chip from Intel. He was my advisor's advisor, essentially. So I guess it's my grand advisor. So this is the adaptation from his lecture that my advisor adapted for his lecture, and now I adapt it for my own lecture. So first of all, you need to understand the past. You know the design trade-off. What's the good and bad thing? This is where your review come in. You look at the previous works and know what's good about that, and what's bad about it. You need to be able to analyze and evaluate previous works, know the future, you have to have vision. Unlike, well, I mean, to be honest, everyone should have vision into, okay, what would be good in the future, right? You need to know the demand for new applications. I'll give you one example. How many of you heard about IoT? Internet of Things, you all heard about it. How many of you actually realize we would discuss about things like scalability and reliability in IoT these days? Do you think IoT would have thousands and thousands of devices connected? Is that a yes? That's a yes, right? You're likely to have thousands of Apple Watches, thousands of a bunch of sensors. If you're not talking about scalability, you're basically bullshitting yourself that you're going to have a working network. You need to scale. If you have vision, you will know that scalability is going to be a huge issue. Reliability is going to be a huge issue, because if you're in a computer network area, you know that each device acts as a possible connection between another devices. What if that device goes down? What if the device goes down? How many times you see a parking meter that has a broken devices? A lot, right? If you go up to a parking like a mall, which don't go there, guys, right now. But if you drive into a parking lot in a mall, sometimes you see those sensors that looks green, right? Oh, there's a parking spot, and you drive there. It's like, oh, there's a car. It's just error, right? So devices that are in the world that have to face the harsh environment of the world, sometimes it dies. How are you going to make sure everything is still reliable? The whole system doesn't crash. So this is what I meant by vision. You have to know what's going to happen in the future, not far in the future, like 5 years in the future, right? And know what would be the good problem. I don't give a, so to be honest, if I talk about IoT, I don't give a crap about how to program it. We know how to program it for a long time. We don't know how to scale that. We don't know how to make them reliable. Those are much more important. Self-driving car. How do you provide a guarantee that the computation that I'm doing right now would be done by the time I hit that object, right? Can I provide some certain guarantee that if I detect something, I need to identify, is that a sign? Is that a human? Is that a tuk-tuk? Is that a dog? Is that a taxi? Is that a car next to me? I need to make sure I have this timing constraint, right? So I can do the calculation on time. Otherwise, the car would crash, right? So these are part of the things that you have to be able to figure out what could go wrong, because you sometimes you cannot afford to go wrong. Right? Sometimes people can die from you writing a wrong code. Knowing the upper layer of the computing stack. So we're going to cover computing stack. Anyone here heard about the word called front end, back end, and full stack developer? Those are just the tip of the iceberg. In the compute stack, there's much more depth into the back end. It just somehow in Thailand, or in, I would say, including Southeast Asia, these full stack developer somehow thought that this is everything in computer and computer science. The truth is there's so many things happening inside that can go wrong, right? That can go wrong. And if you know the thing beyond it, if certain things actually come like and happen and go wrong, you know how to fix it. So you also need to know the lower layer of the compute stack. You want to know the software, and you want to know the capability of the current technology and what will be the future technology, right? I'll give you one example. There's a lot of new technology coming from material science area. We are looking at different devices. We're looking at different properties of new material that we can use as a computer. Why do we care? Because we can have fancy new toy. Well, actually, these are not toy. The fancy new tools that are much either super energy efficient, so we don't go die, like all die because of global warming, or fast, right? Or have a lot of capacity. You can now have a terabytes of memory rather than gigabytes of memory. Who wouldn't want that, right? It sounds awesome. So here's a compute stack. So if you're looking at basically full stack developer, they're kind of like looking at just these 3 boxes: problem, algorithm, and convert to a program. The best thing they can do is to configure it so that you can actually make sure it runs. But in a real computer, there's so many things that happen. When you compile the program, there's a lot of science going into how to make it fast. When you run the program, there's a lot of science to go into how to make sure you can control all the threads, right? Muhammad, you already talked about how you realize that, hey, Windows and Linux has give you different control over different threads, right? The truth is, you are the one writing those code, so you have the option. So if you know how to write kernel code, you can write your own version of Windows and your own version of Linux, so that you can have all the control, right? And why are these important? Actually, if you look at future technology like IoT, for example, you have to be able to write kernel code because you have to control each of the devices. They don't have all the resources so that you can install Linux on all of them. No, somehow you have to write just micro program so that it runs, right? And so that it can communicate. Then you have to figure out, okay, how do I prioritize each of the devices? Who would control the whole system and things like that. And then for folks who are from the electrical background, now you're going to be more familiar with the circuit side of things, right? How resistor works, how capacitor works. So we are kind of like the bridge between the two. We are essentially the bridge between the two. The design choices that we do, anything we do right here, you can see that it would impact everything on the top, right? The software programmer would like have to figure out, okay, this new chip has this capability, and what can I do with it? How many people here know about or have heard about the security chip from the Apple iPhone? Yeah, so if you watch the launch, like basically every single year, right, there'll be an event that launch new iPhone. One awesome thing about iPhone is they have their own security chip. It's a hardware design attached to a memory, also attached to your CPU in the iPhone, to make sure that every transaction that are related to your personal information that you want to make sure it is kept private is protected, that even the iOS has no idea what they are. It's protected by the hardware rather than the iOS. That's why you can, that's one way you can make it super secure, right? And if I put in that hardware design, I need to inform the programmer, say, hey, this thing exists, call this function, because it will make sure everything is protected. Call the function that would utilize the hardware chip, right? So these are fancy new things and fancy new tools that we push out. But every time we have new tools, we have to inform the people at the top of the stack. And basically what we do is link gate and wires to the computer codes, essentially. And this is the power of abstraction. Essentially, as you have more people want to code, right? Do you have to know what's going on inside a computer? The answer is no. Ideally, as a programmer, I want to make sure I can just program in Python, right? Easy, that's all. And I want to make sure my Python code is really fast, right? So this is the power of abstraction. You might not want to know how the instructions are executed. What if I run the same code on a different machine? So why are they slower? Why are they faster? Why do I use Python versus C++? And somehow C++ is faster. How do I have to control each transistor individually? Most of the time we abstract it for you, for the programmer. So why should you care? If I can abstract everything from the programmer, why should you care about the hardware? The thing why you should care is, what if code runs slow? Consume too much energy. I'm sure you all run into these things before. I run a code and it's slow. I play games and it's slow. I play games on my mobile phone. In half an hour, my battery is out. You switch to a new computer. You thought it's going to be faster to run that same program. Somehow it's slower, right? Sometimes program produce incorrect results. You run into seg fault. So if you do homework 0, so you might run into seg fault as well. Your code somehow make computer hangs or shut down a computer, right? Knowing how computer really work can help right here, because a lot of things that I'm explaining here is a part of the computer system and computer architecture area. When we design computer, there are certain assumptions, certain requirements that the program have to meet. If you break that assumption, it will break down, right? Some of the obvious real world example, you can do block matrix multiply. And everyone here is familiar with matrix multiply, right? It's a math function. Which application use a lot of matrix multiply? That are a big hype right now. Machine learning. Machine learning is all about matrix multiply. So what if I can have a hardware that do matrix multiply about 100 times faster? What would it mean? It would mean I can do machine learning. I have a much better throughput to train things, to do inference, to actually use and run machine learning applications. What if you can do matrix multiply really fast, like on a GPU, right? So that's one way you can have a hardware to accelerate a program. So I actually this is true. Basically, the machine learning area that you've seen right now is become useful. Even I'll use the word useful. Actually, it's not even successful. It's remotely useful. It's because of the advances in hardware. We built machines that's capable running so many more matrix multiply per minute that you can actually start using machine learning algorithm to train things. Otherwise, the performance is crap. Otherwise, the performance is actually not as good as using traditional method to detect certain things. Other example is security. I'm not sure if you heard about these 2 bugs called Spectre and Meltdown. It's one of the bugs in hardware that impact how the chip industry behave, because you can have program running and software and antivirus software cannot detect what's going on, but you can attack the other program inside the computer because of the hardware bug. And this is another example coming directly from my advisor's lab. So when I was at CMU, we discovered this bug in hardware. It's actually inside the main memory. If you read to certain parts in the memory often enough, you can flip the data that you don't own. You can flip the other program's data. This problem is called row hammer. And this is another major bug that happened in hardware. That if you want to read the original paper, let me know. It's actually my friend's paper. And this is actually discovered almost by accident, because we are trying to do experiment on a different project. And my friend Young-Gu Kim found something weird that happened. So he looked and investigated, like, oh, this is a major bug that affects like most DDR DDR4 DRAM. So we write the group write a report, publish the result, and suggest certain things that you can do to kind of like alleviate the bug. This is another example. I'm not sure if you're aware of DNA sequencing. So you're in the orientation slide. I talk about this a little bit. So this is a part of the work in that I work in collaboration with a team at Intel Labs, ETH Zurich, CMU, on how can we do DNA sequencing in hardware. The reason behind that is we want to make sure this technology can be used in much cost, less cost, right? So if you are sick, so that you can afford to sequence your own DNA and see if it's likely that you're going to get cancer or certain things. and you can do what we call personalized medicine. Personalized medicine is basically to have a way to treat your illness based on you, your own person, your own DNA, right? Because with mutation that we have, that's why I look different from all of you. That's why, say, we have different heights, different build, even different sex, to be honest. This is like part of our gene, right? So you can guess that then each person will be susceptible for different type of disease. COVID, for example, we don't even know why some of the people that got COVID have severe reaction, and why some people got COVID and almost has no symptoms, right? This is because we are different. Humans are different. So if we can sequence DNA really, really quickly, it means that people can afford to actually get better treatment. So here's a design that all done in hardware to actually make sure that our solution is, I think, about 500 times more energy efficient and about at least like 20-30 times faster than a software solution, even the state-of-the-art solution, and a lot smaller. So you can take a device that are not as huge as an entire computer cluster, right? Take that device and use it in a remote hospital, or like you don't have to be in a big hospital to actually use this kind of thing. So this is another huge research direction that's still going forward. We are trying to figure out and work with the medical industry to see how we can make it possible, right? With the mRNA vaccine, we might be able to kill cancer. Actually, this is another good thing about mRNA vaccine, not just COVID. There's already also papers that propose like we can use mRNA for cancer treatment, HIV treatment, right? These major advances in science is always good. Why is this important? If you still don't care about research, I want to graduate a master's degree and work in the industry. So if you know this class, if you know material in this class, you know, okay, how do I optimize things for performance? Most programmers in the world know how to produce correct results, right? I can program, I can code, and that's going to be correct. The program is correct. I would say less than 1% of the programmers nowadays can write code that are fast. If you look at the entirety of the programmer, or those who claim they can program, I would say less than 1% know how to write fast code. And fewer than that know how to optimize that fast code again. You can actually be the guy who knows, say, for example, the hardware, how the hardware works, to make sure you can write programs that take advantage of the hardware to actually make it even faster. For service guarantee is more like your self-driving car example, where can I guarantee that I'm going to finish to detect, is that a cat, is that a human, is that some random sign before I hit that object, right? How can I guarantee I'm going to finish my function calls or like my program runs in certain amount of time? For energy, writing a mobile application, this is extremely easy. How many people who write mobile application care about battery? Not many. Are they important? Yes. I want to make sure my program doesn't drain battery, right? Writing energy efficient mobile app is not easy for cost. If let's say you own a startup company, when should I replace my server, computer, phones, right? When does it make sense to replace a phone? How can I know the trade-off between this Android phone versus the iPhone, right? iPhone specification sounds like, yeah, it's not just powerful CPU, but somehow if I buy an iPhone, it would last 7 years and it will still be fast somehow. If you buy a Android phone, within 3 years, you will feel that, hey, this phone is slow, right? Why is that the case? If you know the hardware, you know the architect, and you know the design behind it, things will start to make sense that Apple's Apple iPhone CPU is actually crazily powerful, right? So the key takeaway here, knowing the hardware and knowing how it works will enable you to be a better programmer. What else? You also know how to read new hardware paper that maybe you can buy and take advantage of it. It enable new technology like modern day machine learning. Things like tensor processing unit and the GPU is there, and you can use it to accelerate these applications. IoT, right? How can you design a hardware to be more power efficient? How can you design a system that are scalable and improve reliability? Even cool graphic and video games. Who here doesn't enjoy really fancy graphic in video games? None, right? I mean, that's one of the reasons why I play video game, even now, right? I still enjoy playing video game. So having new generation of the GPU that can allow me to render really fancy looking environment, right? It's awesome. There's also a high demand. So a lot of people would discourage students from going to computer system because they'll say, hey, but you have no job, right? But you did not realize, so many of those people did not realize that if you know computer system and computer architecture, a lot of major companies like Google, Facebook, Amazon, Microsoft, Intel, NVIDIA, Apple, many major companies need these skill set because it's one of the area where not a lot of people knows about. A lot of programmer has close to zero knowledge about how computer actually works, so that you can be a better programmer. Right? Basically, once you're a better programmer, you're more likely to be hired by the big computer company. Oops, same slides. And you can do things like optimize popular workload, make ML faster, make AI faster, doing beyond what 99% of people can, right? In Thailand, you can go and check those who claim they know machine learning. Check how good they are. Make sure you know that whatever they produce, at least make sure they can produce accuracy that of at least a little bit better than what if I just took random model and apply it, right? If you apply machine learning, but your solution is not better than flipping a coin, it means that your ML model sucks. It doesn't matter if you know machine learning or not. If you cannot really produce a model that have a good accuracy, then it's worthless, right? I'll use another example. Why would you spend millions of money, like millions of Thai baht, to buy a fancy GPU if you can't really use all of the processing power, and you can do the same with a cheaper GPU, right? So that's it about the motivation behind why you might want to enroll in this class. Now I'm gonna go into the detail what is computer. So let's take let's do a 10 minutes break. I think we have time. So let's do a 10 minutes break. We'll meet again in 10 minutes. Is that okay?
Yes.
Okay, and in the meantime, feel free to type question in on the chat. I'm gonna get some more water, and I'll be right back. Okay.
Okay.
All right. By the way, while we are taking a break, if you have any questions or you just want to chat, let me know. Just turn on the microphone and chat. Cool. Are you guys back? No. Okay, so let's resume our lecture. So I'm gonna move on to talk about what does the computer really is, right? So this is a dictionary definition of the computer. Electronic device for storing and processing data, typically in a binary form, according to instructions given to it in a variable program. All right, long things. But it's a pretty good definition. Why? Because first of all, you can use computer to store data, right? It's a files, raw data that you read, input data from your keyboard, or even input data that are coming from the file, right? You use it to process the data. The difference between computer and a calculator is explained here in the storing part. You punch in the number in the calculator, you do computation, you process the data, and that's it. But you don't program them. You store both the binary data and the instruction given by the program. Basically, it's a machine that can run program. The program is designed to process data. So that's why I think this is a really, really great definition of a computer. So you look deeper, is actually, if you somehow can have a really, really powerful microscope and look at the chip, right? Essentially, these are logic gates. Logic gates are responsible for computation. Then you have a control signal. The control signal are another set of logic that perform our coordination between all the logic gates, communication, including coordination. And you have the storage elements. Typically, these are capacitor and non-volatile cell. Non-volatile cell like SSD and hard drive, they're not capacitor, they are actually different material, but we use all these things to store data in a binary format, ones and zero, right? Physically, these are also transistor, capacitor, resistor, and wires. So one thing I can do, if I know that I need to store binary data, right? How can I store it using electrical signal? I can assume if I have high voltage, it's a 1, low volt, like 0 volts, 0. That's a value 0, right? So you just turn voltage value that you measure into a binary format, 1s and 0. It means that if you can control a series of voltage before you measure the voltage, it means you can have a running computer because you can run and measure binary number. And then you can perform logic gates, perform operation on the binary, which means I have a Turing complete computer. Basically, it's functional computer, right? And if you think about it, it's just a bunch of bits. But somehow they mean something, right? Somehow they run a program. So in this class, we're gonna go a little into how can we actually make that possible, right? So if you look deeper, here's one of the more important side of a computer, processor side. You have the control and the data part. We're gonna expand this in the next lecture. But think about it this way. This is where you process the data. If I have elements that I can process the data, what's missing? Where do I store the data that I'm gonna process, right? And even with that, this is where your program and your data is located when you run it. When you're not running your program, then you have things like storage, hard drive, and SSD. Input-output devices like keyboard and mouses. These are external interface so that you can interact with the computer, right? And with these 3 boxes, you have a complete running computer. So we're gonna go into so in this class, we focus on the left 2 boxes, the processing and the memory. We're not gonna talk about the I/O because that's a different concepts that we would have to expand more into this in order to understand how the hard disk work. So just think of I/O as like your files in a computer, your program in a computer that you haven't run yet, keyboard and mouses, right? And they have interaction between these elements. Oh. Digital computing has been there for a while, right? But before the concept of like electric-based digital computing, you have things like mechanical calculator or Jacob's loom, which is the picture I show here. This is from Wikipedia. You see this card, right here, with a bunch of holes. Anyone want to make a guess? What does this card do? So a loom is a device where you put threads together and make clothes out of it. So so in Thai, it's basically เครื่องทอผ้าครับ เครื่องทอผ้า. So this is like a machine that you put threads in and comes out the clothes. These cards are actually programs that you can use to feed into the machine. And you get different pattern. These line here, we call one line a warp. And you see this in GPU. You see this terminology in the GPU. The warp in this machine is a collection of threads. It's a collection of threads that makes the pattern. So you see the same context again in the GPU. So it's borrowed from this actual machine that allow you to put together a bunch of threads into a piece of clothing that you can sell, right? So this is way back in the history, right? This has been around for a long time. It's a technique that humans use to program how do you want different pattern on the piece of clothing. So that's where the punch card come from. You might also heard about the ENIAC. So there's a picture of a real machine at University of Pennsylvania. I got a chance to visit the university. And this is a picture I took. Sorry about super yellow color. Back then my camera is cheap, so it does look yellow. I think you can see reflection of myself and my friends in the mirror. So this is a machine that many people consider this like first ever computer, right? if you go to Wikipedia, you see that ENIAC is the first ever computer. So this is invented by Eckert and Maury. It weighed 30 tons. It can compute 20 decimal digit word, and it's programmed using all those switches that you see inside this machine. So you just plug and unplug this different wire in order to program, right? So imagine if you had to be a programmer back in the day, I probably like how my brain exploded, because first of all, these things are heavy. You have to actually connect this wire to program, right? And then you only have a few bytes of memory that you can manage to program. These days you have gigabytes of memory to store your data. Imagine what if you have 100 bytes of memory, right? So this thing is a lot more limited and not as powerful. But back in the day, this is one of the most powerful machines in the 1950s and 60s. It's been there for a long time. So in the 40s and 50s, actually, there's quite a bunch of hardware advances. I can actually claim that computer architecture is one of the oldest areas in computer science and computer engineering, because we built machines. We basically built everything that you use nowadays. So there's quite a lot of hardware advances. For example, the ABC, which is one of the major machines, C3 and C4, CC machine. This is actually the machine used by the German, which actually get bombed afterward during the war. So these are the machines used in the World War II, and they actually get bombed, if I remember correctly. The Colossus, which is invented by Alan Turing. I'm sure you know about who is Alan Turing, right? We use his name as the recognition for the prize called Turing Award. Anyone here heard about the Turing Award? So Turing Award. So have you heard about Nobel Prize, right? Nobel Prize is the biggest award for a bunch of areas like physics, I think chemistry, biology. There's also like a peace Nobel Prize, which is like kind of weird, and economy, right? Turing Award is like the Nobel Prize for computer scientists. It's the biggest award in recognition of who we all consider like a father of computer science, right? So he built Colossus. Anyone here watch the movie Imitation Game? So in that machine, that's not the Colossus, that's called the Bombay. That's another different machine that he helped build along with his colleagues at the lab, right? So the Bombay is also invented to crack the German code. The Colossus is another machine that Turing invented to also crack the German code. So if you watch old movies, no, actually not old movies, like movie that reference to this day and age, you might have realized that in a war effort, right, there are three major allies players: the US, the UK, and Russia. Right? They are all allied power that helped win the war, right? There'll be a kind of like almost a meme where the Russian provide the body, UK provide intelligence, which is basically everything that they try to crack, right? So to make sure everyone has information, and then the US provide this factory power to send in like supply. Basically, so the war is won by the three major powers, which all contribute in a different angle. But the Russian would be providing the most soldiers essentially, and then the UK would be the one that focus on the intelligence, the angle of the war, and the US would be like, okay, because they are in a different continent, right? They definitely provide both. Everyone provides soldier for sure, but they also provide a lot of like tanks and parts and supply to the allies. So if you look at the UK during the time, a bunch of computer advances actually helped winning the war, right? And then you saw ENIAC. This is another different machine. EDVAC, invented by von Neumann. Von Neumann is another huge player in computer engineering area, where he invented, for example, the von Neumann model, which we're gonna talk in a bit. So he kind of like paved the way for modern computer science. So so SAC by Wilkins. Wilkins is another major play. So these 40 and 50 is like where we actually basically these guys, we put them on the pedestal. They're like up there and kind of like the founding father of computer as we know it. So IS by Bigelow, and then after the 40 and 50, afterward, once we have the hardware, guess what? We now have the emergence of software. Right? We have Fortran in 1954, and then we move on from Fortran to C and to C++, Java, Python that you use nowadays, right? And the other important thing that we have to kind of touch is the age of Moore's law. You might have heard about the word Moore's law a bit. Basically, Moore's law doesn't dictate, but Gordon Moore, which back in the day he owns Intel, kind of predict that the number of transistors in the integrated circuit is gonna double every couple of years. And inside Intel, there was like a meme, basically to say, well, because the owner of Intel dictate that, we need to make sure we reach it, right? But this is basically, if you plot the trajectory, we are actually following Moore's law pretty closely. Right? We are able to fit in more and more transistor. If we can fit in more and more transistor, it means that we have more parts to build a computer. So we can have more a powerful processor and faster computer. So this is a paper back in 1965, and even nowadays we still try to cram transistor into the processor. So why? You might now be like, why do we care about transistor? Why? What's the difference? Program always want more performance. Performance come from additional logic gates that we put in, additional compute elements that we put in. Transistor is the basic building block for those logic gates. So the more we can cram in, the more things we can do for the computer. So this is one of the resources that we can put in a chip to address certain performance bottleneck and make computer faster. So we can rinse and repeat, right? So this is one of the reading that I'm gonna ask you to read. There's a bunch of options for the first week. It's actually pretty easy. This is one of the paper that you can pick, written by Yale Pat, and it's actually talk about. So this is a paper in the 2001 to be precise, and Yale Pat talk about how the bottleneck shifted, and what should be the problem that researchers should focus on. One thing that I want you to be aware is, because this is a paper from 20 years ago, think about how many of those predictions becomes true in the modern day computing, because you'll find that a lot of things actually turns into the true things. Like these bottlenecks exist, and new chip actually address the things that Yale had predicted 20 years ago, right? So this is why this is one of the required reading. On modern computer, you might have seen many types of devices, such as a Raspberry Pi, right? This is the embedded processor that is capable of installing Linux. You can even use this to like emulate like Nintendo Wii or like PlayStation 2 and plug your monitor to the Pi and play games, right? You can use Raspberry Pi to do many powerful things. And the size is so small. This is GeForce, I think 1080, which is relatively old now. I haven't updated the slide with the new GPU, but it's gonna look kind of similar anyway. So this is a graphic processing unit. What do we use it for? I use it to play games. Many people use it to run things like machine learning or high performance computing application. For example, DNA sequencing, modeling the temperature and predict the weather for the tomorrow and things like that, right? Would there be any benefit of better accuracy for weather prediction? Yeah, huge benefit. If I can predict when it's gonna rain, right? It's gonna benefit the farmer. It's gonna benefit the fisherman who have to go out to the sea and have to figure out, will I die in a storm in the next day, right? Where do I go to make sure I don't die, right? This is another example of a computer. This is a cluster of computer. This is a high performance cluster of computer at Lawrence Livermore National Lab in the US. Right. So these are machines that typically, for example, you want to predict the weather, you run it on a machine like this. It will do a lot of complex operation as much as possible within a limited time frame so that you can predict how's the weather going to look like tomorrow, where's the wind is going to blow into the cloud into, will we die of global warming in the next 50 years and things like that, right? By the way, that's a huge problem for us going forward. Here's another example, the iPhone, right? Is a really, really, really powerful piece of hardware, right? You can use it to run. Actually, this actually can be powerful in most laptops you can afford to buy. The CPU is powerful. It's actually is designed to have a GPU. It's actually have neural processing unit, which would perform certain machine learning function call, right? So you can design to be small and fast and energy efficient. You can also have the things like the GoPro. Unlike the iPhone, this is different in the sense that you now know there's only one application you're running, right? Unlike the iPhone, which run many, many other things, right? So now you can have a much smaller chip, but much more powerful signal processing and video processing processor. Put it on the GoPro and make sure it doesn't break. Now you can have a relatively cheap action camera, right? And quote on relatively cheap, it's not that cheap, but it's a really, really good action camera, right? So you can take it skiing, even though the temperature dropped to like below 0 degrees Celsius, it won't break. This is actually hard to make sure it won't break in a freezing temperature, because most of the time, if you reduce the temperature too much, the battery will not be able to produce as much of the power, right? So the peak power drop with the temperature as the temperature go down. So in this case, you have to design around that. Any guess about this? So anyone heard about a quantum computer? So this is a picture of a quantum computer. This is another emerging area that people predict that some of the application would be replaced by quantum computer, things like security application that demand a lot of non-polynomial algorithm. So if you're taking our algorithm class, you in a few weeks you will learn about this thing called non-polynomial and why they are bad for performance. Quantum computer and the algorithm around quantum algorithm has been almost proven that you can use it to address non-polynomial time algorithm. So there might be a lot of programs that would benefit from running from inside a quantum computer. That's another emergence field in computer hardware. The other thing that I want to make sure you are aware is what happened when I run this simple program. I say I is 10, J is 20, and I just want to add the two numbers together, right? So essentially, this is a program, right? So we are now at the program inside my compute stack. Then you have to compile the code, right? In this class, in a few lectures, we will learn that after you compile the code, this language that human understand, the C code here, will be transformed into assembly. Assembly is a language that computer understand. Computer will then understand, oh, okay, I just need to assign 10 to I, 20 to J, and then add them together, right? What else? The compiler, if they do optimization properly, this code will be converted to no assignment to I, no assignment to J, it's just K equals 30. There's actually a lot of research work into how can we do that in compiler, right? So we can even convert this to K equals 30. Runtime system is, think of Windows and Linux. When you run the program, how are they being managed? How are they being run, right? If I have this program running alongside another Chrome browser that I open YouTube, I have a bunch of tasks that I have to do, right? How does Windows figure out which task should be run next? Should I run this program right now, or should I run the thread that ensure YouTube video is still going and I can still processing the H264 encryption so I can see the video, right? So all this thing is a really complex orchestration of a bunch of programs, right? Think of the OS as like the conductor in an orchestra, right? Everyone has to play their parts. The conductor makes sure the whole thing sounds like proper music. The better conductor, the better music you're gonna get, right? The ISA now we are turning into the hardware side, right? The ISA and the microarchitecture is the one running the program. Think of it as a musical instrument, right, in the band. So the better instrument you get, the more you can get out of your music. In a big band, in a big symphony, right? What do you require to get the best out of everything? Obviously, you need people, right? Think of it as a program. You need good program, first of all, so that you can have a good musician that play the violin, that play the flute, that play viola, that play cello, the expert, right? To play those instruments. But can you give them cheap instruments and expect a great music out of them? No, right? You need to give them tools, proper instrument. Then you also need to give them proper conductor too, so that they can put the music together and come up with a piece of great music, right? So that's what the compute stack is for, to actually produce an awesome piece of program. You need to be able to kind of optimize it from every single part here. Now I'm gonna start to wrap up the lecture. As I said, today it's gonna be lighter. It's a lot of intro, right? So the first material that we're gonna cover is called the von Neumann model. This is really easy to understand. The concept is we call this a store program computer. What does it mean? What does store program mean? I store my program in the memory. That's it. Whenever I want to run something, that program has to be in my memory. What is a memory? Anyone here don't know what a memory is? Is that the gigabyte thing that you buy from your computer, laptop, and phone? Like that number that say I have the memory this size, like 16 gigabyte of DRAM, 4 gigabyte of DRAM, 8 gigabyte of DRAM. That's your memory. That's where you store every single running program. So every program, when you hit enter and run it, or you double click a program, or when it runs like new tab on Chrome, the program get copied over to the main memory. That's why I think like if you have a Chrome, like 30 Chrome tab on your computer start to get slower and slower and slower, right? Because each tab occupies your memory, and at some point you run out of memory. Von Neumann model makes sure the program is stored inside the memory. Why is that the case? The key property is program is stored linearly in the memory. The memory is unified between your program and the data of your program. So when you process the data, those are also in the main memory. Why is that good? It basically makes sure that everything you have to access is in the memory. Every single thing that you have to do with the program will be in the main memory. You can go there and access them. They are available. You just have to go to the right place to get your data and to get your program. And it applies what we call sequential instruction processing. You go that word by word. Instruction is a part of the program. Sequential means that I go first line, second line, third line, fourth line. Does that make sense? If you write a program, it would run the first line, followed by the second line, followed by the third line, followed by the fourth line, right? Easy, right? You don't have to, basically the way you write it is it's the same way as how the computer process that. This basically means that if I write a program that consists of 1,000 lines of code, it will start with line 1, followed by line 2, followed by line number 3, followed by line number 4. The only exception is if you have things like if else. If you have if else, then if it's true, you follow the next line. If it's false, you jump to another line. These simplify how you can build a computer. This actually simplify how you can run a program, right? There'll be this thing called program counter. The program counter essentially points to the current line that your computer is running. The only thing it does is point, hey, that's the line you're supposed to run right now. Once you finish, you go to the next line. You will then point to the next line. This basically the task of the program counter is to point to the current line that I'm supposed to run. That's all. If you have this abstraction, it's much easier to build a computer. It's much easier to build a computer. So that's the von Neumann model. And that's why it's so important, because every single machine you have follow this model. The other model, and this is how it works. So input, which is your program, go to the main memory. Your program counter would access the program inside the main memory and proceed line by line. When it proceeds line by line, it will produce the control unit to do the add, multiply, subtract, and everything you write in the program, and then produce the output, right? And then my question is that the only model? No. In this class, we'll learn how the programmer can still use the von Neumann model. But inside the hardware, we'll try to imitate a faster model. It's a faster model called the data flow model. Von Neumann is the most dominant. So all major assembly code follow this model. x86, which is Intel, follow this. ARM, which they say if you buy the Apple Mac, the M series of the MacBook, they'll use ARM processor. Anyone here has PlayStation and PlayStation 2? They use MIPS processor. So back in the day, those games, they also have MIPS as an option. Spark and Alpha and Power are for, so Alpha is the older ISA, Power is for IBM machine. So if you buy IBM the supercomputer, they'll use a Power architecture. So these are different assembly languages. Think of it as assembly has its own version of the language. There's version for x86, another different version for ARM, another different version for MIPS. We'll go into these in detail in 2 lectures. I think it's next lecture, actually. So what's the alternative of the von Neumann model? The alternative is called the data flow model. And this is actually also really easy to understand. And data flow model is designed for performance. So if you can imitate data flow model, your processor is going to be faster. Von Neumann instructions are processed in a control flow order, line by line by line by line by line. Instruction pointer or the program counter will just get the next instruction, the next instruction, the next instruction, right? Simple. You go instruction by instruction. Mostly sequential, line by line by line, except if else or for loop, where you go jump around in your program. Data flow model is different in the sense that if I know that my 3 instructions has nothing to do with each other, right? I can run them in any order. If I run instruction like line 1, then line 2, then line 3, you are going to get the same results as running line 3, then line 2, then line 1. Or line 2, then line 3, then line 1. So what does it mean? You can dispatch these instructions at any time, as long as they are independent from each other. So this is the data flow model. You start to run the instruction whenever my input is ready. Think of instruction as a function in maths. It's a mathematical function, right? If I know the value of my input, I can run that function regardless of where that line is in my code. I mean, think of it, basically it's as simple as that. I have a function that performs some computation on my data, right? And if I can have all the inputs ready, I can run that function anytime. because it's going to produce correct output regardless. So that's the data flow model. There's no instruction pointer because everything will be based on, do I have my data? Do I have my data? Oh, I have all my input data. I'm going to run it right now. It's as simple as that. The ordering of when you run each line will base on, do I have my input data? If I have my input data, I'm going to run it. That's all. That's all. Think of how you solve mathematical function. How do you do it? You have X and Y and C and A, B, C, D as your input variable, right? And then once you know, oh, X is 5, Y is 10, you would then replace X by 5, Y by 10, and you start performing the computation based on what data becomes available. Same way. So these allow many things to be executed at the same time because there's no ordering between instruction. You don't have to go line 1, then line 2, and line 3 anymore. If my line number 3 has all the input I can run, then 5 seconds after line number 2 got all this input, then I can run line number 2. So that way you can run line number 3 without waiting for line number 2. Why is that good? Faster, right? If you know future instruction has all its input, you don't have to wait for earlier instruction to finish. You can just run it ahead of time. It gives you parallelism. It gives you performance. So here's an example of the data flow model. So let's say this is my sequential program. I do C equals A plus B, then followed by X equals B multiplied by 10, then Y equals B plus X, then C equals C plus Y. You would then realize that this line and this line can be run together, right? If I know A, if I know B, I can run both lines at the same time, which is what you can see right here, right? Both lines we run at the same time because there's no dependency. I mean, I don't care. They happen together, right? There's no dependent input. Can I run this line and this line along with it? No, because I need to wait for X to finish, right? Otherwise, I don't know what X is. I also have to wait for Y. Otherwise, I don't know what Y is. So I have to wait in that case. So in here, data flow would allow the first 2 instructions to be done in parallel, and it would dictate that the result of the multiply, which is X here, would go into the next adder and put B inside. That will produce Y, which go to the last operation, which is the add, right? So you know C, you know Y, now you can compute. And that's all. That's how data flow works. If you look at this example, let's say each line here costs 1 second to finish. Sequential model would take 4 seconds, right? It would take 4 seconds because I have to go line by line by line by line. 4 steps. But data flow model allow you to do the first and the second step together because I know that I can do them together. There's no dependency, right? So it would then, in this case, take only 3 seconds. That's why it's faster. Which one is more natural as a programmer, though? Sequential one. Sequential one is definitely more natural. You go instruction by instruction, line by line. It's easier to program. So if you talk about data flow nodes, there are multiple types. If I'm going to draw a figure, right? So there's a lot of things like computation, which is just input into an operator. Relational, check if A is greater than B or A is less than B or if A is equal to B. Conditional is I have an input. If true, trigger this part. If false, trigger this part. Basically, if true, do this. If false, do this. And the true false is based on the input coming from the horizontal direction. And barrier and sync is basically, I'm going to wait until every one of this input arrive before I proceed to the next step. That's why we call it synchronization, is because I have to wait for all the input to arrive before I can do the next step. Here's one example. I'm not going to talk about. So this is your take-home exercise, right? So figure out what does this do. So here's the exercise. I'm gonna post the slides. We will talk about this exercise in the next lecture. Think about it. Think about what does they do. I'm not gonna grade whether you get the answer or not. So prioritize your homework 0. If you don't have time, no worry. We're gonna talk about this next lecture anyway. So we'll go through this together. But if you have spare time, take a quick look and see what does they do. My hint is do the left side and the right side separately. Right. So and start with some example. Let's say A and B are some binary number like 110 and 111 and see what turns out as the output, right? But 2 things that you're gonna get if you try this exercise. First of all, it's not easy to come up with this data flow. As a programmer, it's gonna be more annoying. So you will then appreciate the fact that you can program in von Neumann. And then we'll let the hardware convert this to a data flow inside the hardware. All right, so before we go, there are a couple of things I want to mention. First of all, the TGS Discord, I'm going to post the link on the announcement in the bit. So I'm going to have to do something. If I have not posted by the end of today, definitely ping me through email is fine. I'm going to post the link. This is an online channel for you guys to just meet, hang out, and basically communicate. Think of it as a virtual meeting room for you guys that you can hang out. Dealing with online lectures, one thing I would like to have is, which is what you did, which is awesome. Like turn on the video and feel free to send me question in a private chat. The reason behind it is because this would allow you to essentially let me know to slow down or speed up. Also to make sure that you want more attention to certain topics. This is the only way for me to get feedback live during the lecture, right? So I don't want to go too fast, and I tend to go too fast. So this would allow me to make sure I don't go too fast. Homework 0 is due next week. So make sure you submit that. This is to test your basic, essentially.